2024 was celebrated throughout India as the centenary year of Bose-Einstein statistics. Now, in the summer of 1924, S.N Bose was a reader in the newly formed physics department of Dhaka University. From there, he sent a paper to Einstein with a request that Einstein should translate the paper in German, and if he found it suitable enough, he should go ahead and publish the paper. Now, the name of the paper was Planck's Radiation Law and Light Quantum Hypothesis. In this paper, Bose had given a theoretical proof of Planck's radiation law for black body. Now, in his derivation or in the paper, Bose had used the idea of light quanta. So he imagined that within the cavity of the black body, light existed as quanta or small bundles of energy instead of stationary waves as had been imagined earlier. And in the paper, he had done the calculations to show how these quanta would be distributed in phase space within the cavity. Now, Einstein was extremely happy to read this paper. He sent a note to S.N Bose saying that it's a beautiful step forward, and he went ahead, he translated the paper and of course got it published. Einstein also applied Bose's way of counting to matter, that is, to the molecules of an ideal gas, let us say helium gas. And he wrote 3 papers back to back in very quick succession. Now, in these papers, he actually predicted a new state of matter at very low temperature. So he predicted that at very low temperature, the particles or the molecules would huddle together, their wave functions would overlap with each other, and the molecules would huddle together, they would lose their independent identity as an independent molecule, and they would behave in a combined manner. Today we call that new state as Bose-Einstein condensation. And years later, in the year 1995, the first Bose-Einstein condensate was obtained in an American laboratory, and 2000 molecules of rubidium, they condensed to form a Bose-Einstein condensate. So that was a triumph of the Bose-Einstein statistics, but neither Einstein was alive nor Bose was alive to witness this new state of matter. But that is only half the story. There is much more to the story than just one paper which I mentioned. Now, so 15 days after sending the first paper, Bose sent another paper to Einstein. And the name of this paper was Thermal Equilibrium of Radiation in the Presence of Matter. In this second paper, Bose focused on light-matter interaction. That is, the interaction of the light quanta with the walls of the cavity. So, what is the fate of that paper? Because that paper also completed 100 years in 2024. So, in this series of Prof Steam Talk Show episodes, we will see the fate of Bose's second paper. And we will now talk to Professor Partha Ghose, who will throw some light on this second paper that I just now mentioned.
When radiation is in thermal equilibrium with matter, its spectrum is described very well by what is called Planck's formula, Planck's law. Now, Bose's first paper was a derivation of this Planck's law by assuming that radiation is like a gas of particles, quanta. We call such quanta photons today, in equilibrium. Now, there is no consideration of its interaction with matter. As long as a gas of photons is in equilibrium, he showed that Planck's law would follow, provided you change the statistics of the photon from usual classical statistics to a new statistics in which these photons are indistinguishable, and therefore the way you count the number of states changes, and that is called Bose statistics. Now, he had written another paper, the second paper, within days of the first one, in which he considered matter as well, that is, radiation in thermal equilibrium with matter. Now, there were two parts to this paper. The first part was to show that the particular mechanism of interaction of the photons with matter is irrelevant. No matter how it interacts, as long as it is in equilibrium, you will have Planck's law simply because of Bose's own statistics. In the second part of the paper, he said, however, photons do interact with matter, and he then speculated or hypothesized that the essence of quantumness lies in the fact that there is a finite probability that even when photons are in contact with matter, they do not interact. Now, this is impossible classically. And he gave the example of a Bohr orbit. An electron goes around a nucleus, therefore it is accelerated. So according to classical theory, it should radiate, but we know that it does not radiate. And Bose interpreted this as meaning that in such states, the probability of interaction of matter with radiation is zero. So from these considerations, he calculated a certain expression for the probability of interaction, which would go to unity when the number of photons in a cell is large, and would go to zero when this number is small. Now, from this, he also stated that the division of the process of emission into two parts, as was done by Einstein, into a spontaneous part and an induced part, is not necessary. He did not say the two do not exist. He simply said it is not necessary to assume this split as a fundamental split. If you assume the spontaneous emission part, then the induced emission part would follow from both statistics and vice versa. And in this paper, he actually gave the example of starting with spontaneous emission alone and deriving induced emission as a consequence. Einstein objected to this. He said that that would contradict Bohr's correspondence principle. But actually, Bose never agreed with that. In fact, everybody who has read the paper can see that this criticism of Einstein was not quite justified. He also gave another criticism, which is that if Bose's law of probability were true, then it would have already been discovered in experiments. Now, that everybody knows that cannot be correct. However, as Einstein said that, because Einstein said that the induced emission, what he called negative Einstrahlung, must be there, and therefore you have to assume that it is there. Bose wrote a third paper in which said, all right, I will assume induced emission and I will show that spontaneous emission comes out. Einstein never even bothered to translate the paper. He didn't even reply to Bose. Now, as we all know, in quantum field theory today, this is exactly what happens. What Bose did is rephrased in modern quantum electrodynamics by saying that there are certain things called creation and annihilation operators, and they don't commute. And so if you start from classical theory, you quantize it, you will get the spontaneous part. Bose did not pursue this matter very much further because he had to go back to Dhaka. See, as I keep thinking about the second paper and whatever Bose had told me, I think the main problem with Einstein accepting Bose's idea was that Bose was proposing that randomness is essential in nature. That is, the interaction is of a probabilistic nature. It may happen, it may not happen. Now, we all know that Einstein did not believe in this fundamental randomness. He used to say, I don't believe God plays dice. Maybe that was also in his mind why he did not accept Bose's paper. But we know today that all quantum physicists later on ignored Einstein. And today, this randomness of nature is well established.
So we see that the second paper, thermal equilibrium of radiation in the presence of matter, is like the abandoned, forgotten twin of the first paper, which is celebrated so much. Now, in the subsequent episodes of PopSteam Talk Show, we will speak to some other scientists who will share their own opinion of the second paper. So keep watching. PopSteam Talk Show is full of surprises.